by Professor Arun Kumar Pati. It's my pleasure to introduce Professor Pati, who is currently the director at Quantum Synergy India and also a former senior professor at Center for Quantum Engineering Research and Education at TCG CREST, Kolkata. He's also an adjunct professor at IISER Mohali, a professor and head of Center for Quantum Science and Technology at IIIT Hyderabad, and Director of Quantum Ecosystem and Technology Council of India, Hyderabad. Professor Pati was formerly a professor of quantum information at the Harish Chandra Research Institute from 2011 to 2023, and previously a scientist at BARC and at Institute of Physics from 1989 to 2010. His research areas include all aspects of quantum information and quantum computation, the theory of geometric phases and its applications, and the foundations of quantum mechanics. Among his important discoveries are the no deletion theorem, geometric phases for mixed state, remote state preparation protocol, the no hiding theorem, and the stronger uncertainty relations in quantum mechanics. Professor Pati has more than 150 research papers and has edited 2 books, one on quantum information with continuous variables and one on quantum aspects of life. So it's a pleasure to have you with us. Over to you. Your talk is titled Quantum Speed Limits for States and Observables.
Thank you very much, Professor Singh. So it's a great pleasure to be here. Before I start, let me thank the organizers, especially Professor Khan and Devashish Khan and Dr. Tiwari, and also Vasudevji and Director Varunji for inviting to this event. So I'm going to tell you about something to do with quantum speed limit, and why I choose this particular topic is I thought this may be something interesting to students, because they can connect to what they have learned in MSc, at graduate level. Okay, so the plan is, with a brief introduction, I will talk about the speed limit for quantum state, and then stronger quantum speed limit, and quantum speed limit for observables, and then some applications of quantum speed limit in context of quantum battery, which is one of the emerging area in quantum technology, and then finally try to summarize. Okay, so when you think of quantum mechanics, as you know, it has been so successful over the last 100 years or so. But then, when you learn quantum mechanics, you see several limitations, starting from Heisenberg's uncertainty principle, which sets a limit on the how accurately you can measure position and momentum and so on. But over the last several years in quantum information, we have found new limitations on doing certain kind of task. So that's what I try to refer here. So quantum physics has several limitations, and that could be due to either operational or dynamical limitations. And from dynamical point of view, you have quantum speed limit. And over last 10 years or so, this has played a pivotal role in quantum computation and quantum control, or even quantum thermodynamics. And these limitations are not only crucial for theoretical questions, but also have practical relevance, as recent years have witnessed the rapidly developing field so-called quantum technology. Okay, so this is where you can connect, what you have learned in MSc level. So you have a quantum system, and you know that system evolves according to Schrodinger equation. Okay, all of you know. Now the question is, suppose initially system is in some state size 0, and you want to reach a state at time t, okay, capital T, okay. And if you apply the Hamiltonian, under this section of the Hamiltonian, system will evolve. But then the question, if you want to ask, how fast system evolves in time, okay? If you want to ask this question, then that's where quantum speed limit will help you to answer this, okay? So here is a pictorial way of looking at this, what is going on. So suppose initially you have the state size 0 and you want to reach at state size t. And if you apply the Hamiltonian, system might be going along some arbitrary path. But then you can connect this 2 point on the quantum state space, technically which is known as so-called projective Hilbert space. And you can connect these two endpoints by a shortest geodesic, and the actual path taken by the system will always be greater than or equal to the shortest path. Okay, so it is something similar to in ordinary, 3D space. So imagine that you have this 3D or 2D plane, and particle moves along some trajectory. Okay, but then the shortest path, and obviously you can see that the actual path system takes is always greater than the shortest path. Okay. And so the speed limit that I will tell you actually follows from this simple geometric, sorry, what happened? Can you make it full screen? Yeah, so, yeah. So quantum speed limit basically is defined as maximum dynamical evolution speed of the quantum system. And if you answer that question, then that will determine the minimal dynamical evolution time you need for a quantum system or state of system to evolve from initial state to final state. Okay. And why this is important? Because this can help to determine minimum time you need, if you want to find out how much time your quantum computer will take to run some algorithm, this can answer that question, okay? In fact, in one of my earlier paper, I have shown that if you apply the speed limit in the context of so-called Grover's algorithm in quantum computing, you can actually determine that square root of n, the complexity, that number of steps you need to determine the particular item in database, actually you can get from the speed limit. And this can also answer the question how much time it takes to a gate operation. And also it can define the shortest possible path and time for implementing the high fidelity quantum gate. And also it can help to design optimal quantum control protocol by setting limit on the speed of the state evolution under external driving force. And in quantum thermodynamics, you can use this speed limit to bound how quickly you can store or you can use your energy flow or information flow in quantum system, essentially influencing the efficiency of quantum heat engine. So it has a lot of applications over the last several years. Okay, so to get the speed limit, what you need is to appreciate so-called geometry of quantum evolution. So as I said, when you have a system and it evolves in time, it traces a path on the projective Hilbert space. And you try to find out how much distance system has gone or traveled during the particular time t, and you will find that the total distance that the system moves, total distance the system takes along this projective Hilbert space, basically integral of the fluctuation of the Hamiltonian. Okay, so that will decide how much length it has, it has gone during this time 0 to t. And once you have the distance, you can define the speed, because speed is nothing but ds by dt, or derivative of the distance. So that will tell you the speed, and speed of the system essentially governed by fluctuation of the Hamiltonian. Okay, so the speed limit that we are talking, over last 10 years or so, but this was already discovered long back by Mandelstam and Tam in 1945. So they proved that if you have a system going from 0 to t, and this S naught is shortest distance that you define like this, take the initial and final state, take the overlap, and that is essentially cos S naught by 2. This S naught is essentially twice cos inverse of this overlap. So that time bounded by h bar S naught by twice delta h. And delta h is basically fluctuation in the Hamiltonian. So this is already proved by Mandelstam and Tam by 1945. Okay. And this is also known as empty bound. Uh, Much later, in 1998, Magnus Levitin, they tried to prove a different kind of bound that is to do with not with the fluctuation, but by giving a bound involving the average of the Hamiltonian H. Okay, so that bound looks like that T is greater than H bar S not by average of the Hamiltonian. So then people thought, okay, which one is better? Okay, then Levitin and Toffoli, they tried to show that if you take the maximum of this or that, and that can saturate the bound. So this they proved that this unified bound is actually very tight. Okay, so how do you prove this empty bound? Okay, I will not focus much on this Levitin, sorry, Magnus and Levitin bound, but mostly empty bound. Okay, so the way you prove is there are two ways you can do it. And one is you use the Robertson uncertainty relation, and using that you can prove this empty bound. And other one is using geometric approach that I just told in the beginning, that the actual distance the system takes is bounded by the shortest distance. Okay, that will give the bound. So if you ask the question, which Hamiltonian can give the optimal, optimal estimate of the time the system takes from initial state to final state. Okay, you see, given two endpoints psi 0 psi t on the quantum state space, there are infinite number of paths you can connect. So not just one Hamiltonian, you can design infinite number of Hamiltonian which can drive the system from here to here. Okay, but then which Hamiltonian will drive the system along the shortest path? Okay, so if you can choose a particular Hamiltonian that will drive the system along shortest path, that is known as the optimal Hamiltonian. Okay, and typically it is very hard, given a generic system, very hard to find what is the Hamiltonian which will drive the system along shortest path. Okay, therefore, a priori is not very clear. So if you apply the empty bound, often you will encounter a scenario where this is very loose for generic non-optimal Hamiltonian. Okay, so the natural question you can ask, is it possible to derive a stronger version of the empty bound that is more tighter than the original empty bound for non-optimal Hamiltonian? That is, given any arbitrary Hamiltonian, can you prove a new bound, okay, which will give the better estimate and tighter estimate compared to empty bound? And the answer is yes, you can do that. And the empty bound is a special case of the new bound that we found, okay? Okay, so already I have mentioned, I think this points, and just to tell you how important this speed limit in the context of quantum computing, people have already found several applications I already mentioned, but the original formulation of speed limit was actually to find the time that the system takes when it evolves from during orthogonal state. Okay, so and that has a natural application in quantum computing setting. Because in the context of quantum computing, if you want to design a NOT gate, for example, or want to take a state from 0 to 1, okay, so how fast you can drive system from 0 to 1, okay, that can answer, I mean, the QSL can answer this question, okay. And Magnus Levitin actually is that 1992 paper, they make a split difference to interpreting the result in the context of number of gate operation in a computing machine that can achieve per second. In Seth Layard in 2000, he also tried to use this speed limit and could estimate um, what is the limit of the computation for the whole universe. And also, as I said, you can use this speed limit to estimate the runtime in any quantum algorithm also. Okay. Okay, let me try to tell you this stronger version of the speed limit that we did. And to do that, you have to use something to do with stronger uncertainty relation that we found in 2014 with my collaborator Lorenzo Meccone from Italy. And this particular relation is a much stronger relation compared to the original Heisenberg, what he proved 1925. Okay, so you can show that the Heisenberg relation is a special case of this particular relation. Okay, so this is that is the reason we call it stronger uncertainty relation beyond Heisenberg. And if you use this, and as you can see why this is stronger, because you see in addition to this term, we have additional term here. And if you choose A to be position, B to be momentum, you have delta P greater than h power by 2 plus something else. Okay, so that is why this is much stronger compared to Heisenberg uncertainty relation. And Heisenberg relation is a special case of this relation. Okay, so if you use this particular relation, you can prove a new bound on quantum speed limit. Okay, to do that, what you have to use this equation of motion that all of you are familiar. Okay, the average of observable evolves according to this equation, and then you choose A in a particular fashion, then you will see the result. So you choose. So forget about. I mean, don't worry about too much detail. You choose observable to be projector onto the initial state, and do some algebra, and then you will see that the fluctuation in the observable A looks like this, and then dA by dt looks like this, and then you use that stronger relation, then you will see that once you integrate this inequality, you will have the bound which looks like this t is greater than h bar s naught by 2 delta h plus something else. Okay, and because this is positive and non-zero, you get a stronger bound compared to empty bound. And if you choose RT to be 0, or if you drop this, you get the empty bound. Okay, so that is the main reason why this is a stronger result compared to empty bound. And not only that, we also prove that if you evolve along shortest geodesic, the extra term naturally vanishes, so you get back to the original result that empty bound already suggest to you. Okay. So to give an example how tight or how good this new bound is, you can work out many examples, but consider a simple example where you have a collection of m number of quantum systems initially in states psi0 all identical, and this n capital N is dimension of the Hilbert space, and this m is number of subsystems. So if you take this example and take the Hamiltonian, which is something like this, and they're non-interacting, and then you can find out the h average, delta h, and so on, everything you can find out. And then if you plot the T by T QSL and T by T stronger QSL, this is due to empty bound. So you see the result drastic improvement compared to the empty bound. So the ideal line is somewhere here, okay? And empty bound, so here this figure is for different n number of dimension and keeping m fixed. And you see that the empty bound lies somewhere here, whereas the new bound is very close to ideal bound. Okay, so you see how good is this stronger speed limit bound. This is really tight, okay, for any Hamiltonian. And similarly, you do the opposite scenario, you fix the dimension and change the number of subsystem. Again, you see the empty bound is very, very loose. Ideal line is somewhere here, and empty bound is somewhere here, whereas the new bound is somewhere here, very close to the actual bound. Okay. Okay, so next is about the speed limit for observable. Okay. And again, students can make connection to what I'm going to tell here. You see, all of you know that you have two different pictures in quantum mechanics. One is Schrodinger picture and other is Heisenberg picture. Okay, in the Schrodinger picture, your state evolves, okay, in time, and observables don't change. Whereas in Heisenberg picture, you have the scenario where states are stationary and observable evolves in time. Okay. Now, the first part of my talk answers the question how fast a state evolves in time. Okay. But if you go back to Heisenberg picture, you cannot apply the empty bound because state don't evolve. Okay. Then what you have to do is you have to ask the question how fast your observable evolve in time. Can you give a bound? Can you give a speed limit on the observable? And surprisingly, even though quantum mechanics is there for last 100 years, this was not answered till 2-3 years back. So we answered this question only in 2022, okay, just 3 years back, okay. So you see, I mean, what you learn in a textbook, as a regular quantum mechanics course, you can still ask interesting questions and try to, get new insights and new results. You see, so that is the beauty of quantum mechanics. So this we did with one of my students. That's what this makes really, interesting. So as I told already, the goal is to look at the evolution of the observable in the Heisenberg picture and answer the question how fast observable is evolution time, and can you give a bound on the speed of the observable. Okay. So once you have this speed limit for observable, it can have a lot of application, starting from operator growth in many body physics or in context of complex systems. You can answer the interesting question that how universal operator growth hypothesis is and how observable becomes more complex over time. So, for example, if you start with a simple observable at time t equal to 0, if you have many body system, at later time t, the observable becomes more complex. Okay, what it means is the following. So imagine that you have a n qubit system. Okay, and at time t equal to 0, consider only say spin say sigma z for the first qubit. Okay, but there is interaction Hamiltonian. Okay, once you switch on interaction Hamiltonian, this observable sigma z for the first particle at time 0 is going to commute with all other observables at other qubit. Okay, but when it revolves in time, the observable becomes more complex, and at later time t, that particular observable is not going to commute with the other observable. Okay, so that is the meaning of the complexity growth in simplest term. But there are more different, more complicated definition you can also use. But this is more simple to understand. Okay, so this notion of speed limit for observable will tell you the maximum rate of evolution of the average of the observable in a given quantum state during dynamical evolution, and that will set a limit on the minimal evolution time that you need to evolve between different average values of a given observable for a quantum system. And as I said, this you did with one of my students in 2022. Okay, so the idea is again very simple. You start with the equation of motion for observable in the Heisenberg picture. All of you know this. Okay, IH by dO by dt is O and H commutator. Okay, this all of you know. So what you do is you take the average of the O in the initial state and use the Robertson uncertainty relation. Then you use the inequality, and then you can show this. And then if you integrate this, you will have the bound which looks like this, and that sets a lower limit, on the time that the system observable evolve between two different, average values. So this is TQSL for observable O. Okay, and we did for different scenario also. If you choose observable to be self-inverse, then you can show this. And not only that, we also did for the mixed state, and we proved different bound. But again, don't worry about details of this, mathematical equations. Okay, so yeah, so what is interesting also, we saw is that if you use this speed limit for observable, you can show that the speed limit for state also follows a special case, in the sense that if you choose your observable to be projected onto the initial state, you can do this little algebra, and also you can show that this t greater than this and this pt basically the overlap of the initial final state. So speed limit for state is a special case of this what we just found. And then, similar to the scenario for the stronger speed limit for state, we also try to prove stronger speed limit for observable. Again, use this relation that with Mekone that I proved. Using that, you can show that T is bounded by something like this, and the eta is sitting here. That eta is, if you recall, that is connected to that extra factor R. And because this is less than 1, this quantity is greater than this quantity. Okay. So this is stronger speed limit for observable. And this we did just last year. Okay. So now I come to the application side. So there are many applications you can think of. So one of the very good application is quantum battery. So it is basically a system where you can store energy, and then you can, and depending on your need, you extract energy to do something else. Okay. And over last several years, a lot of work is going on. And quantum battery can easily outperform classical battery because several quantum advantage you can see there. And as you can see, you can design quantum battery using a many-body quantum system with several degrees of freedom in which you can deposit energy or extract energy or work from it. Okay, so once you have quantum battery, you can do many things. It can have a scenario where you can store energy much more efficiently, and you can use atoms or molecules or even qubits to do things. And you can have a faster charging because quantum speedup can result in quantum parallelism, and entanglement can be used to collective charging of multiple quantum batteries simultaneously. And collective charging is also possible. So instead of charging each quantum cell individually, you can charge this collective interaction that will result in a rapid and efficient charging process. And once you have the quantum battery, you can use quantum field limit, and you can answer the question how fast you can charge your quantum battery. Okay. Uh, so I will give a simple example. Consider a quantum scenario where this battery Hamiltonian is HB, and that is driven by some charge Hamiltonian SC, and total Hamilton looks like this. And for this particular system, you can define how much energy you can extract from quantum battery by unitary operation, okay, which is often called aggregate of quantum battery. So the energy you can extract basically is HB average in state side T minus HB average in the initial state, okay. And as I already I think mentioned this, so application a lot of applications you see, but there are few challenges in quantum battery because to really have a scalable quantum battery, you need to address the issue of decoherence, because the quantum system is very fragile, and any interaction to external world can lead to decoherence, and that can disturb the quantum state, and that will completely spoil the efficiency of energy storage. And other issue is scalability. So if you want to really have a large scale application, you have to maintain coherence, and also to maintain the entanglement for many-body quantum system that you want to store energy. And once you have, once you're able to address these two issues, you can really, make this quantum battery more useful in near future. Okay, so if you use this speed limit for observable, you can use and apply in quantum battery contrast. You can find a bound on the T minimum charging time that looks like this, and also it has different bound for different mathematical quantities. Again, don't worry, this is norm, operator norm, and Hilbert spin norm, and trace norm, and so on. But basically, we will use this inequality to illustrate some simple example. Okay, and you will see how good this bound is. Okay, so yeah, I will finish in 5 minutes. So you can use the stronger speed limit for observable to give and bound on the minimum charging time of quantum battery. Okay. So prior to our work, already there are several work and people use charging time of quantum battery, and they are based on distinguishable quantum state like initial final state. But the bound we present is based on difference of initial final agotropy, and that bounds can be easily, this new bound can easily outperform previous bound. Okay, so here is a simple example. Consider 2-qubit cell. So you have a HB plus H interaction also, and HB looks like this. Charging Hamiltonian looks like this, and interaction Hamiltonian looks like this. And this empty state is down, down, and full state is up, up. And this has this energy levels. If you take this model and then apply our bound, you see how good it is. So the charging time versus this TQSL. So ideally, we would a straight line, and our bound actually just sit on top of that. Whereas if you use the bound that we did in 2022, that is slightly lower than this. So the stronger bound, if you use, that is really tight, and the same thing you see here also. So this shows that the stronger speed limit for observable really, outperforms the speed limit that we did before. Okay, so now I try to summarize what I said. So quantum speed limit is a very important notion, and it plays a major role in quantum theory, in quantum computing, quantum information, quantum control, quantum thermodynamics, and many other scenarios also. So what I try to do is also try to prove a new bound, which I call stronger speed limit for unitary evolution of a quantum system using stronger uncertainty relation. And then we prove that the empty bound is a special case of this stronger speed limit. And not only that, we try to prove also the speed limit for observable. And also we prove a stronger speed limit. And then the standard speed limit for state can be viewed as a special case of this observable speed limit. And then we use this stronger speed limit for observable to answer this or to determine the minimum charging time of quantum battery. We found that really able to capture this charging time more precisely. Okay. So with that, I thank you and continue to explore unexplored. Okay.
Thank you very much, Professor Pati, for this very interesting talk on quantum speed limit and its importance. We appreciate
Thank
you
you.
understood well.
Mhm.
Yeah, could you give some
What time?
numerical estimate? Maybe you mentioned, I missed. What is a typical time scale? Is it like a nanosecond, or when you say quantum speed limit, it's a unit of time, no?
Yeah, here is, I mean, we have made it time dimensionless, but it will depend on the system parameter, like, how much your driving force or driving field and so on. So depending on system parameter, that might change. Yeah.
Yeah, so some ideas like what is the ballpark?
Yeah, I mean, again, this will depend on the, that should be within the decoherence time, like in dependent system, like superconducting qubit.
It would not be on the scale of minutes, say. or
Yeah, microsecond could be.
It could be, yeah. Could it have played an important role on how quickly life evolves on Earth? Like
Yes.
mutations, how quickly mutate? It could be significant there also, is it?
Right, right. Yeah, if we try to, I mean, if you can somehow model that quantum mechanics plays a role in mutation, certainly you can apply the speed limit and try to answer how efficiently, how fast this mutation takes place. Yes.
Has it been studied?
No, not yet.
No,
Not
it
yet.
could be
Not
interesting.
yet. Yeah,
Yes.
definitely. Yeah. Yes.
Yeah.
Yeah.
Thank you. Thank you.